Hello, in this video we'll give an introduction to probability. So let's start with our working definition for probability. So we'll say that the long-term proportion in which a certain outcome observed is the probability of that outcome. So a key part of this definition is long-term proportion. So something that goes hand in hand with this is called the law of large numbers. And this says, as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer and closer to the probability of that outcome. So if you think about, for example, tossing a coin, on a single toss, you can either get heads or tails. If you toss a coin 3 or 4 times maybe, it's possible that you would get 2 heads and 2 tails, and that may lead you to believe that there is a 50-50 chance for each of those outcomes. But that's not guaranteed. It may be that you would just happen by chance, maybe in 6 coin tosses, to have more heads than tails, maybe 4 heads and 2 tails, which might lead you to believe in that case that there was a 4 in 6 chance of getting heads. So in order to rely on proportion to get closer and closer to probability, we need to conduct an experiment many times, have many observations, and in the long term, the proportion will say get closer and closer to the true probability. So if we do this hundreds of times, then or maybe even thousands of times, then the proportions of heads is going to get will be the actual probability for getting heads in a coin toss. All right, so let's talk about some of the vocabulary that we use in a discussion of probability. So first of all, one thing I've already used here is probability experiment. So that was part of this definition of the law of large number. So in probability science, we say that an experiment is any process with an uncertain results that can be repeated. And so tossing a coin or flipping a coin is an example of an experiment. So it's a process with an uncertain result. We don't know what's going to happen on any given coin toss. It's one of 2 things, but we're not guaranteed heads or tails. If we were guaranteed a certain outcome, it wouldn't be an experiment. So we need uncertain results, and it needs to be we need to be able to repeat the process. So tossing a coin, that is something that we can do over and over again. Another common example in discussions of probability is the roll of a die, where there are 6 possible outcomes. You can have 1, 2, 3, 4, 5, or 6 on a single roll of a die. And so this is certainly something on a single roll we don't know what's going to happen, so that has uncertain results. And you can certainly do that over and over again. So those are both examples of probability experiments. However, I don't want you to think that probability experiments are always about sort of like games or games of chance. Another example would be, let's see if you pick a student at random and ask their college major. So another example might be, so I'll call this example number 2. Maybe you are able to call someone randomly and ask and you could really fill in the blanks here, but let's say that we're going to ask, do you intend to vote in the upcoming election? And so, that's when I pick someone at random. I don't know what their response is going to be when I ask them their college major, and I can do that over and over again. I could stop or pick different students, and I'd likely get different results. Same thing with calling someone. I don't know ahead of time what their intention would be about voting, and I can certainly do this over and over again, so I'm able to repeat this process. Another term that we use in probability is sample space. So the sample space is the collection of all possible outcomes for a probability experiment. Now, when we are tossing a coin, the sample space, there are just two possible outcomes, heads or tails. When you're rolling a die, there are 6 possible outcomes. So this is their sample space. If you pick a college student and ask their major, there would be lots of possibilities here. And when you ask someone if they intend to vote, there would be they may say yes or no, or they may be undecided. The notation that we use for sample space, first of all, we indicate sample space with a capital S. And because this is a collection, we use set notation. So we start with a colon and then a bracket. And then you can list the elements that are in this collection. So for instance, in the coin toss, I can use an H and a T to represent heads or tails. So this is the sample space for this experiment. For the roll of a die, I might do this. So here I'm listing the possible outcomes on a single roll. For this example of calling someone asking about their intention for voting, I might limit their responses to yes, no, or undecided or unsure. And so there might just be those 3 elements. If we take a collection that may not be all of the possible outcomes, we may end up with an event. So an event is a collection of outcomes. And I'm going to just say here, not necessarily all outcomes, in which case it would just be the sample space, but often it's just some of the outcomes. So we will use set notation to define events, and we can name an event using a capital letter. We wouldn't want to use S. So for instance, let's focus on the experiment of rolling a die. And so maybe I'm interested in the outcomes that are even numbers. So I might define an event and call it A, and then list the elements that are in this event, 2, 4, and 6. Those are the even numbers. Or I might construct another event and call it B, and that may be the 3 larger outcomes, 4, 5, and 6. And so, there are lots of different events that we could construct by pulling elements from this sample space. If you just pull a single element, one outcome, we often call that a simple event, and in which case we might use a lowercase letter like E, and just say that that's just maybe the outcome 1, or another simple event might be the outcome 6. And so what we're then ultimately interested in, though, is the probability of an event or a simple event. So I want to start a list of what we'll call the rules of probability. And so our first rule is going to be that any probability is going to be between 0 and 1. So the notation for probability, I'll use a capital P and some parentheses. And then I'll use whatever letter or however I've named an event, I'll put that inside the parentheses. So for instance, if I've named the event E, I'll put a capital E inside the parentheses, and this means the probability of event E. And so that's always going to be between 0 and 1. Now, if you prefer, you could certainly say between 0% and 100%. And let's see, and also, if we take, for instance, let's just say we have a sample space, and it's a collection of simple events, and I'll just use subscripts to say this is the first simple event, this is the second simple event, the third, and so forth, maybe up until the last in the list of simple events, and I'll just use a subscript of n for that. So the second rule of probability says that if we take the probability of each of these individual outcomes or simple events, and we add those together, then this sum has to total to 1. So if you conduct the experiment, one of these things is going to happen. And so that's where we have, there's a 100% chance of that. By the way, this is a good point for me to say, in probability, we say that if an event is impossible, the probability of that event is 0. And if an event is certain, it's guaranteed to happen, then the probability of that event is 1. In everyday use speak, sometimes when you say that something has a probability of 0, there's a 0% chance. In everyday use, you may interpret that to mean that there's just a very, very small chance. It's very unlikely. But in the science of probability, that a probability of 0 really means that something's impossible. It cannot happen. And a probability of 1 or a 100% chance means it is guaranteed to happen or certain. Another term that we use in describing probability is, say, if an event has probability less than, I'm going to leave a little blank here, we say the event is unusual. Now, I'm not filling in this blank because the way that we define unusual can depend on circumstances. But oftentimes we'll say if an event has a probability of less than 5%, or sometimes we'll say 1%. In rare cases, you may even use something as high as 10%. Now, which of these that you choose can depend on the circumstances. For instance, let's say when I was asking somebody their college major, and maybe in a certain environment, a math major is unusual, so maybe less than 5% of students are math majors. So that might meet my standard of unusual when I'm talking about college majors. Now, if I were doing a medical study and maybe testing a drug, and I found that maybe 3% of people who take an experimental drug have a very adverse and severe reaction. Well, in that situation, 3%, 3 out of 100 people are having this, bad reaction. To me, that is not sufficient to qualify as unusual. That's a little bit too much. In that situation, something where I'd hope for unusual might be, less than 1%. So, all right. I'm going to continue on with one more definition, and that is a probability model. And so this lists the possible outcomes of an experiment and each outcome's probability. So there are those two pieces, the possibilities and their probabilities. Oftentimes we do this in a table, and so we'll list the outcomes and the probabilities. So for instance, in a coin toss, the possibilities would be heads and tails, and the probabilities we know are 0.5 and 0.5. So keep in mind that when you're constructing a probability model, in order for this to be valid, you'll have to make sure it meets the conditions of rules 1 and 2. So as a reminder, rule 1 says all the individual probabilities have to be between 0 and 1. So notice these values are between 0 and 1. And that second rule says that when you sum the probabilities, you should get exactly 1. And notice that if I add a total here, 0.5 plus 0.5 is exactly 1. So I'm going to stop there, and I will continue on in another video with some methods for computing probabilities.